I'm Bobby Eshleman. I'm a software engineer at Vates, and I work on the XCP&G team, which is our open source distribution of Zen. Um, by the way, is my audio pretty good? I sometimes have microphone issues here.
Yeah, we can hear you.
Yeah, we can hear you. Okay, great. Um, so I want to talk to you about enabling UEFI Secure Boot on Zen. We'll talk about really briefly the rationale for UEFI Secure Boot. There's a lot of other talks that go into that very well, so I'll just kind of uh, be brief there, and then talk about how UEFI Secure Boot works, what support exists in Zen today for that, and kind of what we want to see moving into the future. So the basic goal with UEFI Secure Boot is just to have a system that's trustworthy, which really just means assurance that the underlying system hasn't been tampered with and it hasn't been changed in some malicious way. And if you want that guarantee at runtime, you need to ensure that that guarantee has been established early in the boot process. So it really something that requires strong boot security. If you don't have boot security, then you can't have these guarantees later at runtime. And boot security really implicates trust at the entire system, at all application down to firmware. So just to give like a brief look at the rationale for that, or how that argument typically goes, is that you can't really trust your applications and what you're seeing at the application level if you can't trust your kernel, because the kernel has the ability to do whatever it wants with an application. It can falsify logs about it. It can extract data from the application. It can change it in this way. So in order to trust what you see at the application level, you really need to be able to trust your kernel. And the same argument goes down to the hypervisor, where the hypervisor has the same power over kernel or guest kernel that the kernel has over applications. And you can follow this logic all the way down through the bootloader, through firmware, and down to the CPU. And CPU trust is obviously a totally different talk, but I wanted to kind of plug RISC-V here because, one, I'm giving a talk on that here at the Zen Summit on Thursday, and there's a lot of work being done in the open ISA world with regards to CPU trust and trusted supply chain for CPU, now that designs are open source and auditable. But really the point of this slide is just to point out that there's work being done actively at every level of the system to give that assurance of trust that we need. So the scope of this talk, and really the scope of UEFI Secure Boot, is to give you assurance of lack of tamper from the OS kernel, hypervisor, bootloader down to the firmware. So what is UEFI Secure Boot? We're going to talk about what it is and how it works. So UEFI Secure Boot is really just an extension of the UEFI spec. It's a boot security technology, and that extension, the intent of it is to simply establish a chain of trust out of first firmware launch. And I mentioned first firmware launch specifically here, and I'll talk a little bit about that on the next slide of kind of why that's important to note. And what this extension does is simply add signature verification for UEFI applications. And in our space, UEFI applications, I got a notification that my connection was lost. Am I still there for everybody?
Yeah, you're still on.
Yeah. Okay, great. In our space, UEFI applications are typically your bootloaders, kernels, or hypervisors. It depends on your system, but UEFI applications can also be like disk encryption utilities, or the Windows bootloader, etc. So the reason I mention first firmware launch, Secure Boot establishes trust from firmware launches because it really assumes that the trust chain has been secured from reset to firmware. So depending on your platform, there's plenty of code that runs before you get to your UEFI implementation. And UEFI Secure Boot does assume that that's been secured. So if you're looking for assurance of those earlier pieces, you need to take advantage of whatever your platform provides for that. That's not going to be something you get just from the UEFI implementation. And another thing to know about UEFI Secure Boot is that it assumes that anything loaded will carry that torch of trust onward, which means that the UEFI spec lays out a particular type of trust model, and when you move execution forward, whatever is executed needs to also have a trust model that it enforces, and it needs to maintain the trust boundaries that are set up during boot. So how does UEFI Secure Boot really work? In the UEFI implementation, there's a boot service called load image, and this exists without the Secure Boot implementation as well. And its job is simply to take an EFI application or an image and load it into memory. And when you have UEFI Secure Boot enabled and implemented, load image will refer to a list of certificates or hashes that it is aware of and verify that image against that list of certificates or hashes. If the image has been signed by the private half of the certificate that is in that store, then it'll be verified and it'll load successfully. If not, it'll return a security violation. So these certificates are protected. They're stored in what are called secure variables in UEFI. And so what are these secure variables? It's important to note how they're stored because if anybody can change them, then that's a problem. Most variables in UEFI are not secure variables. If you have firmware access, you can change them to whatever you want. You can append to them, you can delete them, whatever you want to do. But in order to change a secure variable, the change that you want to make needs to be signed. And there's a couple of different ways to do this. Basically, there's generic secure variables, and then there's those that are specific to Secure Boot. And we're going to look at those specific to Secure Boot. But this property of changes to secure variables need to be signed enforces the ownership and privilege policies that are built into the Secure Boot spec. So what are the secure variables that are relevant to Secure Boot? The first important one is the DB variable, which is just a list of certs and hashes. If your image is signed by a key whose public half is in the DB, then it'll be verified and launchable. You can also just take a hash of an image and load that into the DB, and that also functions. But obviously that will require a lot more space to do that for every image that you want. So usually it's just a cert or a list of certs, and you sign the images that you trust with the private bit. Now, let's say you sign something and a vulnerability is discovered in it. You want a way to revoke that, and that's what the DBX variable is for. There's also a list of certs or hashes, so you can take a hash of the thing that you've already signed, load that into the DBX, and then it'll be revoked whether or not it's in the DB. So that's really the revocation mechanism for things that are discovered to be not trustworthy. And then there's the KEK, the key exchange key, which really defines who's able to modify the DB and DBX. It's also a list of certificates. And then there's the PK, which is a platform key, which says who has control over the KEK, and that's also a certificate. So the scheme between the PK and the KEK is really a way for trust to be given to another party or delegated. So as a platform owner, you have control via the KEK, and you can say, okay, well, I trust Microsoft or whoever you want to trust, and you can load up their KEK and give them the ability to modify the DB or DBX on firmware update or so it's tying those variables back into like how Secure Boot really works. It's that load image boot service refers to the DB and the DBX when it goes to load an image. So if you've got your image signed, it'll be fine unless it's in the DBX phone, then it'll be rejected. So I'm going to take like a little detour and kind of talk about Microsoft's role as a signing authority in the kind of the great UEFI Secure Boot world. Their position as a signing authority is kind of important if you want to target the so for us with XCP-NG, we're a distribution, and we want to function on as many platforms as possible. And a lot of platforms will have the configuration that I'm about to go into and talk about. And it primarily exists because Microsoft has a hardware certification program that is that, okay, if you want to ship with the Windows logo on your UEFI implementation has to ship with these certificates in this way. But I also wanted to note that the next couple slides might not be relevant to you if you have access to firmware or if you have access to the firmware vendor or hardware vendor, then you might not need to use Microsoft as a signing authority because you have control of these certificates. So this is a very typical certificate configuration that you'll find is that the PK is really owned by the hardware vendor. The trust model, as it's kind of talked about in the spec, seems to imply that the platform key is owned by the person who owns the machine. But in practice, it's often just the hardware vendor that ships with the PK. But there is also always the capability for users to change these things themselves. That's also built into the certification program. So then the KEK at least includes usually Microsoft KEK certificate. And then the DB includes two Microsoft certificates. One is the Windows Certificate Authority, which they use to sign all of their Windows-specific binaries, like the Windows bootloader and kernel, and etc. And then there's this third-party certificate authority, which is used to sign driver or UEFI applications. And most relevant to us is to sign bootloaders for other operating systems. So that's kind of the situation you find yourself in if you're a distribution or you're wanting to get some third-party software working on widely available platforms. And Microsoft and other parties enable this by this project Shim. And Shim it's one software project that's maintained by various people. You see all the Linux distributions involved with it. I think it was originally a Red Hat project, but Microsoft has an expedited process for getting Shim signed. So it's really the path forward for any distribution or any other third-party software. And what it is it's an EFI application or a PCOF application. And all it does is load and verify bootloader or kernel. And what this allows is that it allows for distributions to embed their own certificate into Shim, and then they get the whole thing signed by Microsoft. And then that Shim can now run on these widely available platforms with Secure Boot enabled, and then Shim will use that certificate to verify the distribution's binaries. So if you have Shim on your system, the boot chain ends up looking like this, where the EFI loader to the DB and see the Microsoft third-party certificate authority, and it'll verify Shim with that. And Shim has embedded in it this third-party certificate, which the private half of which is used to sign the bootloader. And then there's a connection here between shim and the boot path from the bootloader to the kernel, and that's because shim also installs a protocol that allows for future applications so long as you haven't exited boot services yet. So here the bootloader is essentially making a call back to shim and saying, hey, I need you to verify that this kernel has been signed with one of the certificates that you're aware of. So this allows you on a consumer hardware platform to have Secure Boot enabled and to have everything verified from the UEFI implementation through shim, through the bootloader, and to the kernel, which is exactly what we want in this case. So the question is, can we extend this trust chain to Zen systems? Which means, can we extend it from the bootloader to Zen and to the DOM 0 kernel? And the answer to that is really yes, but only on some Zen systems. So I'm going to talk about what Zen systems are capable of doing this and which are not, and plans to make all of them capable of this, and work in progress there. So here's these two configurations. Well, here's the first one. The first one is just the Zen EFI binary. Zen outputs two different binaries. There's the multi-boot 2 capable one, and the one that is a PCOF binary, which is a EFI application. And it being PCOF makes it signable and then verifiable by the EFI loader and the shim verifier. And so it's in a format that they understand. If the Zen implementation as an EFI binary, if it detects shim, it'll use shim to verify the DOM 0 kernel. So there is that extension of trust up to the DOM 0 kernel, which is exactly what we want. The only slight limitation, depending on your code base, your product, your project, is that like in our case, we do still support BIOS. So adopting Zen.EFI means that we'll then have to maintain two different binaries, which might be a bigger problem for some people or a smaller problem for others. It's just something to note that it's something that if you have Grub in your boot chain and you're mainly using it for cross-platform support from BIOS to UEFI, then you'll have to maintain a second binary here to make Secure Boot possible. And then the second one I wanted to talk about is the unified binary, which uses the Zen.EFI. But what it does is it allows you to take your kernel, NNRD, your configuration, which contains your command lines for Zen and the kernel, your XSM policy, microcode, all of these things you can bundle into a single binary and sign the whole thing. And then when the EFI loader or shim verifies and loads it, you've essentially verified all of the boot modules that you want to verify. Cryptographically, it's been verified to be tamper-free. And then Zen will introspect to find each of these boot modules and load them accordingly. The slight limitation there is the same as before. Obviously, EFI binary is not going to work on BIOS. And hopefully, if as few users using BIOS as possible. That is a hope. So what about multi-boot 2 Zen? Does it support Secure Boot? Currently, it does not. And that's really for two reasons. It's not a format that the EFI loader understands. The EFI loaders are not multi-boot 2 compliant. And then it's also not in a format that the shim verifier understands. So the shim verifier requires that the payload be a PCOF application, because the PCOF specification basically says where the security directory is, where the signatures are stored. So the shim verifier doesn't understand Zen and V2. There was previous work done by Daniel in 2018 to support the shim protocol in multi-boot 2 Zen and get it, apply a peakoff header. And we picked that, patched that up, and rebased it to head and integrated some upstream feedback into it. But there's still work there to get that upstreamable. And we're also talking about maybe an alternative route of introducing a multi-boot 2 header into Zen.UEFI. But there might be some complications there because Daniel had tried that back in 2018 as well. This is all just to say that there's some work being done to get to the point where we have a single binary that will boot on BIOS or UEFI. But if you happen to be on UEFI and you happen to have Secure Boot enabled, then it'll just work similar to the way that a lot of Linux distributions do. Let's see where I'm at on time. Okay, so assuming that you've got your system set up to where the boot chain is secure and your verification goes all the way up to the DOM0 kernel, does Zen really support UEFI Secure Boot at that point? And the answer is not quite. And the reason for that is that Zen systems really need to be locked down. And lockdown seems to be a term picked up from the Linux community. There's been a lot of work there done on this specifically for Secure Boot enabled platforms. But really what lockdown is implying is that at runtime, the system software is doing everything it can to prevent the subversion of the protections that Secure Boot enables. So like as a really super rudimentary example, let's say you have your secure boot chain in place, everything's been verified, and then a privileged user can just launch via kexec any arbitrary binary that it wants to. Clearly that nullifies all the benefits you get from Secure Boot. But at a less rudimentary and less simple example, there's also a lot of ways that a privileged user can mutate or change the kernel at runtime or change the hypervisor at runtime. And so one way of looking at Secure Boot is you've guaranteed that the entire boot chain has been immutable. So it has preserved this property of immutability. And then at runtime, you're just letting a privileged user do whatever it wants to it while it's in memory. And that's obviously a violation of the trust model that's been established, which is that your kernel, your hypervisor, all these things are unchanged. So our DOM0 kernel is Linux, and so we're going to be kind of using that as a model moving forward. Each different type of kernel that is used in DOM as a DOM0 or as a privileged domain will have to implement its own mechanisms for preventing users from taking advantage of these capabilities that really should be delegated to just the system software on a Secure Boot system. So I'm going to look at just kind of what type of stuff that Linux kernel lockdown does, and then also look at what that means for Zen, the type of things that Zen will need to do, and that's all future work. We have a kind of informal working group to discuss those problems, and people in the community that we can work designs out and get some of this done. So I just wanted to put that out there. That is future work, but we kind of have a high level of what we need to do. So on Linux kernel lockdown, things that are restricted from privileged user space that are not otherwise restricted include things like devmem, which would allow you to modify physical memory, or kmem, which gives you access to kernel virtual memory, or IO ports. You can't use BPF because then you're essentially just running code in kernel. PCI bar access could be a vector to modify the kernel or compromise it. ACPI table manipulation are all things that lockdown prevents. And these are all things that we want to be prevented on Zen systems as well. Beyond just restricting the ABI, you all have the requirement that live patches, kexec binaries, kernel modules all be signed, because those are all things that are entering into privilege space or kernel space or hypervisor space. And so they need to be signed. So you're going to see a very similar list with the things that we need to do for Zen. Seeing if this has, okay, cool. So for Zen, we're going to need to do something similar with live patching, kexec. Some of these things might be taken care of by kernel lockdown itself. Some of them might need further work in Zen. And then you also have sensitive ABI operations that are specific to Zen. So you've got the ability to modify your trap table, modify your page tables with MMU update, set GDT. You've got map manipulations. A privileged user can modify the view that the kernel has of physical memory, and that is obviously a violation of the properties that you want from a secure boot system, that the system has been unchanged and uncompromised. And there's a lot more there. These are all through the devzen privilege command ABI. So we're going to want to do things like this, and also probably maintain all of the restrictions that are in Linux kernel lockdown. So yeah, that's my overview of where UEFI Secure Boot is at and work we're getting underway. And so there's just a list of links of things that are relevant, and I guess I'll open it up to questions.
It does occur to me that we might be able to create a zen.efi that also has a multi-boot 2 and a multi-boot 1 entry point that BIOS scrub could pick up. So at the moment, irritatingly, those headers are present and point to junk locations. But I don't fundamentally see a problem with being able to create one binary that can still boot in both modes. It's obviously not the one we've got at the moment, but I don't think that's impossible to do. So that at least gets you back down to maintaining one binary.
Yeah, I think... sorry, you go, Jan.
Quite recently, this was discussed a second time on the mailing list. And Daniel pointed out, again, I simply forgot about him pointing out the same fact earlier, that the layout of the PE binary does not easily lend itself to the requirements that either of the two multi-boot formats require, because the bootloader wants to put the binary flat into memory without regard to arrangements that differ in disk layout versus in-memory layout.
Right, multi-boot 2 is the implementation is happy if the file layout is different than what the layout will be in memory.
So in the end, this is, as I understand it, also a reason why we have to push zen.gz in the process of creating it through the funny make elf32 utility. That has not only the effect of marking it as an x86-32 binary, but also that the disk layout and in-memory layout match.
So we would maybe need to have a similar utility for expanding the file layout to what it'll be in memory, correct?
Yeah, that is one of the possible routes to go. The problem there is that this would increase the binary size by quite a bit because of the 2 meg alignment of the text, read-only data, and writable data sections. And all this padding would need to be accounted in the image already.
Right.
So
Well,
yes, Andrew, it is not in principle impossible, but I'm not sure it is a desirable route to go. We'd have to see how it ends up.
work to be done. Well, we're at time now, so great. Okay, cool. We'll wrap it up. All right. Well, thanks everybody.
Thank you very much.